The electric grid, it's just one of the most incredible things we've ever built. A sprawling, interconnected machine that keeps our entire world humming along. But deep inside this machine, there's an invisible heartbeat, something that has kept it stable for a century, and it's starting to change. I mean, think about it. For more than 100 years, this whole system has operated like a massive, perfectly synchronized orchestra, with every single power plant spinning in perfect lockstep across thousands of miles. It's a miracle of electromechanical harmony. So what's the problem? Well, the very nature of that harmony is being rewritten by all these new energy sources. And that creates this silent but really profound challenge to the stability we've all just taken for granted. Okay, so to really get what's happening, we need to dive into the grid's original heartbeat, this incredibly powerful spinning force. And that heartbeat, it comes from this thing, the synchronous machine. Seriously, just picture a gigantic spinning top, a huge chunk of rotating metal that's physically and magnetically locked to the grid's frequency. These things have been the absolute backbone of our power system since, well, forever. And right at the core of this machine, you've got the rotor. That's the part that's actually physically spinning. And yeah, its main job is to make electricity, but it's the sheer physical momentum of all that spinning mass that is the secret sauce for grid stability. In that momentum, well, it has a name, inertia. It's all that stored energy from the rotation. It's a lot like a heavy flywheel, right? Once it's spinning, it really doesn't want to speed up or slow down. It just naturally resists change. So here's the best way to think about it. Inertia is literally the grid's shock absorber. If a huge power plant suddenly trips offline or a massive factory fires up, all that physical momentum just soaks up the shock. It gives the whole system these precious few seconds to adjust. It's a stability system that's built right into the physics of the machine itself. Pretty cool, right? And that brings us right to the silent challenge we're facing today, the rise of modern renewable energy. Okay, look at this. On the left, you've got our old-school synchronous machines, heavy, spinning metal. On the right, modern solar and wind. And these are all about power electronics and software. Now, the key difference, and this is everything, look at that bottom row. Zero physical inertia. There's just nothing physically spinning to act as that shock absorber we were just talking about. So this leads to a really simple and honestly kind of terrifying question. What happens when the grid loses its shock absorbers? Well, the system becomes more brittle. It's more vulnerable to sudden changes, and that means a much higher risk of instability. The good news is engineers saw this coming a mile away. So the first line of defense, it was basically to write a whole new rulebook for how you connect to the grid. And you can actually see that evolution on this timeline here. It really started back in 2003 with the first standard, but the rulebook has been getting smarter and smarter. The really big leap, though, was in 2022 with this new standard called IEEE 2800. This one sets a whole new, much higher bar for the big renewable projects. So what are in these new rules? What do they actually demand? Well, at the end of the day, they're telling renewables, hey, you can't just be a passive supplier of power anymore. You have to actively support the grid. You need to ride through faults, which just means you stay connected during a problem. You have to help stabilize the frequency, and you have to prove with computer models that you're going to be a good grid citizen before you even plug in. But, new rules are only half the story. The really cool part is the technology. I mean, how on earth do you teach a silent, motionless piece of electronics to act like a giant spinning machine? Well, you do it with this brilliant piece of tech, the Virtual Synchronous Machine, or VSM for short. It's this super smart inverter that uses some really advanced software to perfectly mimic the physics of a traditional generator. It basically creates what we call synthetic inertia. You get all the stability, but with none of the spinning metal. It's awesome. The company Safery put it just perfectly. They said a VSM simply behaves as if it is a spinning synchronous generator. It's like a digital ghost in the machine, and it's providing that stability we've been losing. And it's not just theory. This data from the National Grid shows just how well this whole mimicry thing works. Just look at these columns. A grid-forming converter, that's a type of VSM. It checks pretty much all the same boxes as a traditional machine. It provides inertia power, it operates in synchronism, the whole deal. Now, look at the conventional converter on the far right. See all those no's? It just can't do most of these critical jobs. And this visual really brings the whole idea home. On the left, you've got the diagram for that big, physical, synchronous machine. On the right, the VSM's equivalent. It's doing the same stabilizing job, but it's doing it with smart software instead of tons and tons of spinning steel. Okay, so this is already pretty revolutionary stuff. But some researchers are pushing the idea even further. They're asking, what if stability didn't have to come from one big machine at all? Not a real one, and not even a virtual one. And that leads to this absolutely fascinating idea called synthetic discrete inertia. The concept is actually pretty simple. What if you could create that same grid-stabilizing shock absorption, not from one big thing, but by coordinating thousands, maybe even millions of tiny, flexible devices, all working together in concert? So what are these devices we're talking about? Well, they're things that a lot of us already have or will have very soon. We're talking smart water heaters, home batteries, those EV charging stations, even flexible industrial equipment. Each one on its own is just a tiny resource. But when you coordinate them all to act like a swarm, the effect is, well, it's profound. Take a look at this chart. It's from a study of the Irish grid. It shows frequency deviation, which is basically how much the grid's heartbeat wobbles when something goes wrong. Without these little devices helping out, the wobble's pretty big. But when you activate that swarm to provide inertia, look at that. The wobble is drastically reduced. So here's the big takeaway, the crucial point. We are witnessing a fundamental shift. The stability of our electric grid is becoming less about brute physical force and these massive spinning machines, and it's becoming all about distributed digital intelligence. It's a really incredible transformation when you think about it. And it leaves us with this really fascinating question to think about. As we get better and better at mastering this new digital complexity just to keep the lights on, what other amazing possibilities is it going to unlock for our energy future?